All right, everybody, welcome back to episode 17 of Uncertainty and Probability Theory, the Logic of Science. Today's episode, random means unpredictable. Random means unpredictable, unpredictable to you. Remember, we're always interested in probability and uncertainty. And probability is about some proposition of interest we pick, given some set of evidence or observations or model or whatever thing we assume. Now, that proposition of interest will be unknown to you depending on the evidence that you assume. So when something is random, it only means that you could not predict with certainty the proposition of interest given the evidence you assumed. That's all it means. There has developed, unfortunately, particularly in statistics, the idea that randomization, we're going to talk about this. This is not going to be the last time we talk about this, but the idea that randomization gives you something, sort of blesses your statistical results, sort of allows you to make these calculations valid. It imputes a validity to them in a sort of almost a magical way, a ritualized way. There's no other real way to put it. Randomization does nothing for you at all. And I'm going to prove that to you over the course of several lectures. But today we're going to go through one simple one and to give you Jaynes' view on this. We're still operating in chapter 3 of Jaynes. Now remember, the proposition or the problem we've been working with last time, we had the hypergeometric function for a given set of evidence. And we developed a approximation to the hypergeometric, which turned out to be the binomial distribution. It's just an approximation. It's a mathematical convenience, perhaps, or perhaps not, depending on what you're going to do with it. But that's all it was. It was only an approximation. So let's review that, and then we'll move on to quoting Jaynes on this kind of stuff. So we started with this information. We have some device, or a machine, or something in the world, or an urn, or as it's going to turn out in a minute, a coffee can, because I don't have an urn, but I do have a coffee can, inside of which are M, red, or we might label them successes, or a 1, or whatever you like, some dichotomous thing, an N total, from which we deduce, or we surmise from this thing, our implicit premise that we have N minus M that are not red. And another way to say not success is a failure, or 0. This is a tacit premise that comes with this. It's pretty obvious. We deduce this. Now, we had the probability, we wanted to calculate the probability, again using Jaynes' notation, of drawing out or measuring, measuring, whatever we like, the very first instance that it will be a red or a success, or however we want to label these. So the very first thing is going to come out, we're going to calculate the probability it will be red. Now, we don't know what it's going to be based on B. And I said in a written lecture last time, only. This is the only thing we know. And I said that if I would come through the screen and I would beat you over the head with this only. And I would. I still would. I want to very much impress upon you that this is it. We're accepting this B. Only this B. In this particular problem, we're accepting this B and only this B. We're going to calculate the probability based on this proposition of interest that we picked. And we're going to calculate the probability of it given this B and only this B, nothing else, no other information in the world. You are free, of course, to substitute this in your own problems with other information, and that changes the probability. And that is the key lesson of this entire course. This entire course is you change the evidence, you change the assumption, you change the data, you change the model, you change the probability. Nothing has a probability. Nothing has a probability. Probability is only in relation to the evidence you assume, because that's the way logic works, and probability is logic. So we have deduced that this is the case. There's m of these successes or reds or whatever you like, and it's m over n. No problem. So now what I'm going to do, and I happen to have a version of an urn here. I'm trying to not to make too much noise with this. It's annoying, but I could not find anything that resembled an urn. But I got a coffee can, and I don't have any marbles or anything like that, but I do have these wire nuts. I don't know if you can see them. I got 1, 2, 3, 4, 5. I got 8 yellow wire nuts, and I got 3 red wire nuts. Okay, so into the urn they go. Let me write this down. So that's our explicit premises. Now m equals 3, n is 11, and then of course n minus m is 8. And so for this particular b, we're just going to augment b with this information right here. This will turn out to be, of course, 311. Okay, no problem. We're going to augment it once more. So what I'm going to do, I'm going to reach in and grab one. Aha, okay, so it's red. We already calculated the probability of this. We have it. Maybe you'll notice what happened right there. Maybe you haven't, but it's going to be clear to you, I hope, in a couple of minutes. Now what I'm going to do is this. Can you see? I can't see on the camera here. Don Pedro. I'm going to put it back in. Now I want to know the probability of drawing out a red again. It's going to be fairly obvious, but let's think about this. So I'm going to augment B. I'm going to have B, this is Jaynes notation, I'm going to have it B plus Boolean notation, drop back in and redo. Or with replacement is the fancy way of saying it. With replacement. So I'm going to take out whatever I have, I'm going to look at it, and I'm going to put it back in. However many I'm going to take out the first time. And I'm going to take them all and put them all back in. Remember the hypergeometric, we can take out however many we've taken out before. We can calculate the probability of taking out however many red and whites that are left, or yellows in this case, with the hypergeometric. Same thing here, but we're going to add this fancy word with replacement. So, if we want to calculate something like the probability of red on the second and red on the first, given this B prime, well, we could use Bayes' theorem. The probability of B2 given R1, oops, not B2, dummy, R2, given B prime, times the probability of R1 given B prime. Well, this part right here is still going to be m over n. But what's this? We have this wrinkle here. We have this wrinkle here where we have this B prime. What does it mean exactly? So let me read to you from Jaynes. He's very clever about this. And I know you know what the mathematical answer is going to be. It's not going to be any secret. However, we need to be very careful about thinking about this, because it's at this point where we rush to the math that we've forgotten what we've done and we start inventing for ourselves these magical concepts. So here we go. He says, in probability theory, there's a very clever trick for handling problems that become too difficult. And this is difficult because we don't know what this replacement does to the distribution of all the other marbles or successes or 0 1s or anything that we have left in the bin or the machine state or anything like this. So we can solve these kind of problems, Jaynes says, by one, making it still harder. It's a very common thing to do. We can redefine what we mean by solving it so that it becomes something we can do. And I've kind of given you hints before. Try to solve a simple problem before you try to solve the more difficult one. Or here's my favorite part. We can invent a dignified and technical sounding word to describe this problem, which has the psychological effect of concealing the real nature of what we have done and making it appear respectable. So what have we done? What have we done? When I pull out one of these things, aha, and I drop it back in, what do they ask you to do normally? We're going to have to randomize. Now what does that do? There are inside this thing caps, these wire nut caps, and they are sitting in there in some way or another. And there is some way or another I reach my hand in and I get them and pull them out. There's a whole host of causes going on and conditions of the experimental setup that we have right here. And so my taking one out and then putting it back in changes those causes and conditions in some way in which we don't know because we're not measuring it. It's not assumed in the information that we have assumed up here. So they say what we have to do is then randomize it. Now what does that mean? Well, it means shaking it around. Okay, fine, we can shake it around, we can mix it up, but what does that now do? How does that change your knowledge of the position of each of these caps inside? How does that change your knowledge of how I'm going to reach in and grab them or anything like that? It doesn't. It doesn't change your knowledge at all. You could certainly add to this bee. I could have a thing brimming full of these wire nuts or something, and I could just place it, I could take one off and I could place it right back on top so we could all see it just resting right there. And then I'm going to grab another one. I can just grab that one. Aha! And then I can say, well, the probability then is obviously going to be not m over n. It's going to be something like 1 because I can see what I'm doing. Because you have augmented this b, which I know, with plus, I know the cause. You know the cause. You know the mechanical cause, the efficient cause of what's causing this thing to be placed into my fingers. Okay? That's all that is. So right now, you just don't know. You didn't know when I picked this thing up how anything was. You don't know anything when I pulled one out. And you certainly don't know anything still when I drop one back in here. You could always add to this. You could always put your own surmise into this by adding something else to this. Now with the I know, I'm going to make that B double prime. Of course, you could always do that. And now I'm going to take a quick pause. All right, pardon that little brief hiccup there. I had to take care of something that was unknown to you and unpredictable. Therefore, it was random. I didn't give you enough information to figure it out. So, if you know the cause, if you know all the causes, then you know. If you could look into this urn, and you could look inside and pick, and you want to pick your favorite ones, of course red is a favorite color, then you'll pick the red. That is an entirely different set of information than this B prime, B, or B double prime. It's entirely different. You change the premises, you change the information. Let me read you again from Jaynes. We often want to have randomization in experiments, as I mentioned to you, but we're going to go over that again when we talk about that and what the supposed benefits are and why I think those benefits are nil, non-existent. What we really want is, as I've mentioned many times, is we want the cause, and we want to have a real control of cause, of the real causes and real conditions that bring about effects. And those are what we're after in science, and probability can get us partly to that answer, but it can't provide the answer. We always bring cause and everything to probability, and it's the same thing with randomness. We bring this information to the probability. And if we say, I know the causes, well, then you can change the probabilities entirely. So one thing that people think they're going to do is they're going to shake. They're going to shake, make a loud racket like that. I hope it didn't destroy anybody's eardrums. That's somehow going to make it more random. Well, it does on the surmise that we know about the behavior of things like this. It does mix up the order. In the sense that it changes the order from what it was to something new. But it doesn't change the probability because the order was completely unknown to you in the first place, and all I've done when I've shaken it around is change the order again. That's it. And so you don't know what the order was before, you don't know what the order is at the end, therefore the probability doesn't change. The randomization is unnecessary. It's the same thing with these so-called randomizers, covered now with chalk dust. The reason that we use these things to produce outcomes that cannot be easily predicted is because we cannot easily control the causes of them. That's why when you go to a casino, for instance, they have these, and this is just a cheap one, but they have very sharp edges on the ones that you get in a casino, and you have to have throws that hit the back wall of a craps table, for instance, and they have to bounce off, all these kinds of things. And that's to ensure that there's absolutely no way that anybody could well, conceivably or knowingly control the causes of these things. And so you make the outcome unpredictable because you don't know the causes. If you don't know the causes, you can't change the information you're conditioning on. So that's simply it and nothing more. So I'll read to you Jaynes on this. Shaking, for instance, discern, does not make the results random. He uses the air quotes too. Because the term is meaningless as an attribute of the real world. That's absolutely right. It has no clear definition in the real world. The belief that randomness, and he again uses the scare quotes, the belief that randomness is some kind of property existing in nature is a form of the mind production fallacy, which says in effect, I don't know the detailed causes, therefore nature does not know them. That's exactly right. That's exactly right. We're saying because you don't know, therefore nature doesn't know. So I could reach in here and shake these around and I can pull out a, okay. I'm going to reach around and pull out a, okay, a red. I'm going to reach around and shake and pull, randomize, pull out a red. I'm going to reach around and shake around and pull out a red. Oh, I'm going to reach around, I'm going to pull out a red. Okay, oh, how can I do that? Well, because I have 2 pots, one of which is entirely full of red, and the other one has some of the yellow in them. And I could switch it up on you. So to me, the outcome was not random. The outcome to me was entirely predictable because I cheated. And that's exactly how tricks are done, magical tricks are done, and so forth. I'm going to link another video I did at a Broken Science event that illustrates this even better. But in order to do that, I need an audience, and I had an audience at the time. You guys are an audience, but it had to be a live audience because I asked them to guess a number that I was predicting. And I gave them, the audience, subtle clues and hints about what that number might be. And I asked them to see if they could pick it based on their own impressions of their own information and so forth. And you'll see exactly what those results were. Okay, there's no homework this time because the math is actually very trivial. Because we have done this, the answer is going to be, as I mentioned in the beginning, because we're putting the things back in, and in B prime there's absolutely no information about the order or the cause or the conditions or anything like this. The knowledge of the first draw is irrelevant because we put the thing back in. So the math is exactly what you think it is. There's no surprises there. There's no tricks in the math and everything. But maybe I'll put, if I can think of something, a good puzzler for randomization, I'll put it down in the comments to this or in the lecture. But mostly I want you to read Jaynes. I want you to read Jaynes chapter 3, and I'll put the page numbers I want you to have up there. That's it for this time. Next time, we're going to go and start finally about what probability is not. And that's going to take us a few weeks to understand exactly what probability is not. We've learned what it is, we've deduced what it is, and now we got to go through all the common mistakes that people make. That's it for now. More information is down below, and thanks very much for watching.